Okay, so let's talk about the category 1, alright, where we talk about the chemistry, where we will not alter any chemistry at all. Okay, so there is a name that calls it is called the transformation hardening, alright, cat 1, alright, more than just now what we have seen just now, modifying surface without altering the chemistry. So therefore, to a more exact name, is called the transformation hardening, alright. And therefore, what is it all about is that you change the phase of your material, alright, the martensitic, or the whatever austenite or whatever. Okay, so you change the phase to a harder and stronger phase, alright, in order to do certain stuff. So you need to quench and temper it, alright, to increase the strength without compromising ductility, etc. So you need to know how to explain these things, alright. And alloys are hardened by cooling rapidly, so you need to cool very rapidly so that it can form the martensitic type structure, so which is stronger, alright, and things like that. So if you want to be a ductile one, then you have to have a slow cooling and things like that, so that to give a ductility and toughness. So fast cooling is give martensitic, which is strength. If it's slow cooling, then it's ductility and toughness, alright. So this process is also applied to carbon steel. So you need to know, in fact, the cat 1 is to alter the phase of the material, alright, the phase. So there's no chemical reaction that occurs, right, because it's just the phase, alright. So therefore, what is the example of one type of so-called cat 1? Okay, so in fact, the one example is actually this one. Okay, so this name is called the transformation hardening. Okay, so it will be here. So there is two types like transformation hardening and special machine like peening and cold deformations. So as you can see, the sharp peening is actually hitting the surface, alright, to change the phase of the surface also. So yeah, so at least you get to know the meaning. So unless there is a question that will ask you to explain transformation hardening or explain one of the processes of cat 1, then you need to explain in details of this thing. So let's take a look on this information then. So like I say in the just now that particular page where we discussed that you need to, if you want a martensite type of structure, you need to actually increase the temperature. So therefore, one way is to have a laser beam. Alright, so your laser beam will shine upon this place where you'll cause it to heat up very fast. So once you heat up very fast, you off the laser beam, it will also cool down very fast. It will cool down by itself because, for example, if you were to heat it to maybe 1,000 degrees Celsius, alright, so the normal temperature in the room is about 30 degrees Celsius. So therefore, once you suddenly release the 1,000 degrees Celsius heat, alright, then you actually plunge down to 30 degrees Celsius as soon as possible. So you generally, the environment will cool it down. So the environment acts as a quenching process, or in other words, to cool the structure over here very fast. Alright, so I repeat again, the environment temperature cools the material very fast. Alright, so you don't need to do anything to cool it. And therefore, this is just the transformation hardening process. Alright, you use the laser beam to heat it up. After you off the laser beam, then you will cool it straight away, and you can create a martensitic structure due to this phenomenon. Alright, hopefully you are clear. And just take note that this is called a substrate. Your substrate is this thing, I guess. Alright, and austenite structure, I also don't know what. As you can see, the martensite, alright, when heated it goes to austenite, and then when cooling it goes to martensite, and then deformations go to martensite, whatever. So austenite is more so-called neatly arranged, I guess. I think right, the FCC, alright, is the austenite. Okay, so in other words, to a more clearer case, alright, if you were to heat up your material, alright, when you heat up at very super fast, like the laser beam as we said just now, you actually put your material into the austenite region. Alright, so when it's in the austenite region and you cool it very fast, alright, the cooling very fast is called the martensitic transformation, and therefore you will form martensite, alright, within this austenite region. Alright, hopefully you are clear. So the austenite is just a region that we observe. That's just the meaning of that. Okay, hopefully you're kind of clear. So oxidant itself, alright, by right it should be strong, because there will be a certain interface where this thing over here will actually prevent the atomic thing to slide across it, so there will be a preventing force. So FCC is stronger than BCC, I think. Yeah, most probably lah. Okay, so hopefully you're kind of clear about this thing. So coming back here, alright, so if you want to cool rapidly, you cause it to have a martensite structure, which is strong. Or if it's slow cooling, about 600 degrees Celsius for 2 hours, alright, using the laser beam, alright, then you'll stabilize the structure and partly restore ductility and toughness. Alright, so in other words, let's say if it's martensite already, you can also change and alter its so-called phase, alright, and change it from a high strength material to ductile and toughness using 600 degrees Celsius for 2 hours. Okay, but generally this is a very expensive process. This is the very high-end process. If you were to take a look on this thing, laser hardening is this thing, alright, but the equipment is very expensive and not economic for large surfaces. Right, for automation, it's straightforward and very precise control can be achieved. So if you want something that is so-called very small surfaces that you want to have it to be martensite, laser hardening is good, but yeah, as you know, it's pretty expensive. So normally people use flame hardening, so you just use a flame gun and you heat it up, alright, but it's quite slow and blah blah blah. You can read yourself. Induction hardening is more on the high frequency stuff. Alright, so this magnetic thing over here will heat up the surface, or it heats it rapidly. Okay, so these are the different types of hardening method that you can do, and these are the transformation hardening process. Hopefully you are kind of clear of Cat 1 now. Alright, well, Cat 2, I also want to briefly talk about it. Alright, what's shot peening and cold deformation. So let's take a look. It's best if you were to watch the shot peening video.
Metal Improvement Company, a business unit of Curtiss-Wright Surface Technologies, is a recognized leader in surface treatments and the application of controlled shot peening. The application of controlled shot peening improves performance, reduces maintenance, and provides a cost-effective solution to premature failure in critical components. Shot peening is a method of inducing residual compressive stress into the component by bombarding the surface with high-quality spherical media in a controlled operation. The media can be steel, ceramic, or glass, and each piece acts like a tiny peening hammer, producing a small indentation in the surface. The application locally yields the material, inducing beneficial residual compressive stress, the characteristics of which are dependent on the base material and component design. At the same time, unwanted tensile stresses are removed. The proven results from controlled shot peening show a dramatic beneficial effect on both the life and strength of components, welds, and materials, making the material resistant to fatigue, fretting, and stress corrosion cracking.
I think you get what I mean already. So shot peening itself is to somewhat improve corrosion resistance, fatigue, etc. Okay. But again, this type of method is to prevent any fatigue or corrosion, etc. So it is good for surface, because shot peening itself is to treat the surface better. Alright, hopefully you're kind of clear. So to better understand shot peening again, or I think another video is also better. I give you the example also.
If a metal is bombarded sufficiently to indent the surface, a residual compressive stress is induced in the surface. When a metal bar is flexed a sufficient number of times, it will eventually start to crack from metal fatigue on the side where the metal is being stretched in tension. However, a crack will not occur on the opposite side, which is being pushed together in compression. So if we could somehow induce a compressive stress on both surfaces, the metal bar could theoretically be flexed much longer without cracks occurring on either side. The shot peening process, which impacts the surface with millions of tiny metallic or ceramic spheres, is a practical and cost-effective method to introduce a residual compressive stress on and beneath the surface. If a flexing load is applied to a shot peened metal bar, the load must overcome the compressive stress from the shot peening process before a crack can start. This can translate to a significant increase in the service life of the part. To re-emphasize, metal fatigue cracks can only start when a metal surface is in tension, never where the surface is under compression. Metal Improvement Company has been a pioneer in developing shot.
So metal fatigue cracks can only start when the metal is in tension. So if everything is in compressive, then you will not have any fatigue cracks. That is just the meaning of that. Okay. So therefore, the shot peening method, right, is in this case is just only to treatment the surface, alright, to treat the surface better. While transformation hardening is a total phase change process. Alright. So I hope that you kind of see the difference between these two methods. And therefore, in the next video we'll talk about category 2, alright, in a way that is more on the chemistry side. So I think see you there.